Hello everyone, welcome, willkommen. I'm Ilan Ilic, and I work as a lead site reliability engineer at Nordeus. Today, I'm going to talk about our Kubernetes Autoscaler, but it's not going to be a sterile architecture textbook presentation. Instead, I will take you deep into the trenches of my SRE team to the point of the time when we were preparing for the most anticipated release ever. It was a high-risk release where my infrastructure team had to ensure that our infrastructure can handle sudden spikes in load from few hundreds to 200,000 matches in a few minutes. A few words about my company. Nordeus is a mobile gaming studio founded and based in Belgrade, Serbia. Since June 2021, we are part of Take-Two Interactive. Nordeus currently has 2 live hit games. One is Top 11, and another one is Golf Rival. We have one more in soft launch. It's called Top Goal. Within Take-Two, we are focused on mobile sports games. Today, we will focus on Top 11, Nordeus' most successful game. And this presentation is about how we made a predictive Kubernetes autoscaler for Top 11's most anticipated release ever. Top 11 is a free-to-play football manager game where you, as a user, once you register, you get your own football club, which you manage. You're changing your squad, changing tactics, formations, you train players, and you compete against other real managers worldwide in various competitions. So just like in real life, we have leagues, Champions Leagues, Cup, and so on. And just like in real life, everything that managers and football players invest into football, it needs to be displayed during the match. And it's the same in Top 11. Match is a core game feature. Everything that users invest, it has to be shown there. So match is a core game feature, and its live match screen has evolved over years in Top 11. In the early beginning, it was a mostly static screen showing some key stats and commentators' texts. In the middle era, it was a 2D pitch preview where football players were represented as colored dots. And finally, in 2022, we released the most anticipated release ever. It's called 3D Live Match, where we show like the most important highlights of the match in a 3D format. What's important to mention about Top 11 live match, it's not recorded in advance. Instead, it's being simulated in real time. And we are not streaming match as a video. It's a custom format. And we are not streaming it continuously. We are streaming only highlights, like the most important parts of the match. And this is how it looks like. Does this work? Just a second. So this 3D live match exists thanks to 3D simulation football engine. Only a couple of groups in the world built full 11 vs 11 football simulation, and Nordeus is one of them. It's a highly complex system consisting of AI, animation, physics, and it takes into account all relevant inputs during the game. To convey you how deep we went into transferring real football experience to mobile game, is that we took real football players, we equipped them in suits with sensors, so just like in movies, and we let these players play real football. So we can transfer everything into mobile game. There is a whole documentary about how we made the football engine. You can check it on YouTube. But today my talk will be about how we are streaming these 3D football simulations at huge CPU scale, how we engineered the solution, and what were the challenges we faced along the way. So our goal was to deliver realistic football on every device. What does every device mean? Our users play on devices that are more than 10 years old, and we still value these users. That's 95% of entire smartphone market, which is about 20,000 different devices, each with different CPU, GPU, and other components. We quickly realized that we cannot render everything on these old devices. Instead, we move it to cloud, and we are streaming these 3D highlights in real time to these devices. But we are not streaming videos, we are streaming our custom format in 50 bytes per second, which our Unity game applications, clients, can render in real time in 3D format. Our another goal was to integrate this new 3D live match into existing, at that time, 12-year-old architecture. And the final one was to guarantee great user experience at any scale. Our users simply don't care about how many CPUs we are burning, how many matches are being played. They just want real football on their mobile phone. There were certain limitations from the early beginning to make things more interesting. One thing is that 3D simulation engine is a single-threaded Unity application which uses 100% of CPU while generating this 3D highlight. Another one is that because this live match is being played like in real time, everything that...
Yeah, just make a little quick wrap up, but it should be okay.
Okay, sorry, I did. Quick wrap up. We have these limitations from the beginning. We had, I think we stopped here, maybe. This one. Here. Thank you. So these limitations are 3D simulation engine is a single-threaded, uses 100% of CPU. Maximum allowed delay is 5 seconds. Otherwise, it negatively influences user experience. And we had a limitation that we should not increase cloud costs for more than 10%. This is how top 11 architecture looks like, but this is a simplified version. We will focus on. It's self-explanatory, I think, and here we can start this one from the beginning because it's important one. So all matches in top 11 are being simulated by match series, and while being simulated, they can be watched by users. And if match is being watched, it listens to manager's inputs in real time and takes them into consideration for the rest of the match. And when there is an important part of the match or highlight, match will request 3D rendering for that important part. It will send a request to 3D simulation engine. It will send it to the queue and wait up to 5 seconds to get a response. On the right side, idle 3D simulation engine instance will consume that request. It will generate 3D highlight, and it will take it about 2 seconds. and it will use 100% of CPU while doing so. After that, it will return response to a queue, which will match consume and broadcast it to all match spectators via edge service. What's important to mention here is that matches will be simulated by match service regardless whether they are watched or not, but 3D highlights will be generated only if match has at least one spectator. This means that 3D simulation engine load directly depends on user activity because we are generating 3D highlights only for matches being watched. So with system like this, it has certain challenges. The first one is that this is a real-time system, and match as a core game feature directly influences user experience. If these 5 seconds elapsed and we skip highlight, it negatively influences users. Just imagine scoring a goal and not being able to see what happened. It's a nightmare. And another one is that simulation is a high compute operation. Simulation engine is a single-threaded application, uses 100% of CPU. Third one is we have high spikes in load, where number of matches goes from few hundreds to 200,000 matches in a few minutes. And as I said, 3D simulation engine load directly depends on user activity and number of concurrently watched matches. And this thing is not fully predictable. We cannot predict how many users will watch these matches. And this is how number of matches varies during the week. And as you can see on the right side, on weekend, it goes from few hundred to 200,000 matches. So our initial idea was to, okay, let's have maximum instances ever needed. It would work, but it would cost us a fortune. And only financially viable solution would be to scale resources based on demand. During many matches and high user activity, to scale more 3D simulation engine instances, and during low activity, low number of matches to decrease them. So our goal was to scale, to teach the system to scale itself automatically. As a preparation, around that time, we just migrated on Kubernetes on GCP. We used GKE there. And Kubernetes autoscaling was a natural choice for us. Another thing, as part of preparation, was to find a way how to integrate real-time system into existing top 11 architecture. We decided to use real-time queues, like a low latency queue, messaging queues. I can come back to that later, why we need messaging queues there. And since the whole Nordeus infrastructure is hosted on Google Cloud, natural choice would be PubSub real-time messaging service. And we tried it, it worked, until the point when we exceeded 2,000 concurrent matches. After that, everything eroded. It stopped working, the latency was huge. We got in touch with GCP PubSub engineers, and we realized that the problem is that at that point, we had more than 2,000 3D simulation single-threaded applications as a consumers, pulling from the same subscription at the same time. And PubSub engineers told us that PubSub was not optimized for that use case, and that we should look for some other solution. And luckily, we found like Redis and made it under 50 milliseconds. Fun fact is that a few months later, PubSub engineers contacted us again and told us that they spent a few months into optimizing PubSub for our scenario, that it will work now. But we already went into production with Redis. We use PubSub for some other part of the game, but here we use Redis. Redis. Because this was a high-risk release, we couldn't just pick up the first solution and go to production with it. Wait for production data to stress test it. Instead, we had to test and iterate with the solutions during development. And before exploring solutions, we got together and aligned on success criteria. And system observability was the key here. We defined the most important metrics along with logs and tracing, but these metrics were important and we aligned on success criteria based on them. We covered everything, like a number of requests sent, number of requests processed, request durations, time spent in queue, number of failed requests, everything. And this became like an important foundation later in production. Also, live match is a complex system, and we had to test somehow all possible scenarios. It's being simulated in real time. It takes into account managers' inputs. So there are many various possible scenarios. And we didn't took like an approach of making synthetic requests because it's impossible to cover all possible scenarios. Instead, we decided to use real production data and test our solutions based on them. We used something called shadow testing, which is something you should consider for your projects. How it works. First, we covered the entire system with all possible metrics, logs, traces, and we tracked everything. Then for regular users, everything worked like before. Matches are being simulated by match series, and important highlights are generated in 2D format, in the old way, and sent to regular users. However, in the background or in shadow, match service was requesting 3D highlights, but these 3D highlights were showed only to Nordeus devices, like a predefined list of Nordeus devices. So this was a nice platform for testing and iterating with auto-scaling solutions without affecting regular users. We could spin and test all possible scenarios without affecting user experience. So you should consider it for using it for your projects. So now when we have the full context about 3D simulation engine and its challenges and limitations, then we have aligned on success criteria and we have a testing platform based on shadow testing. Now let's explore how to teach system to scale itself automatically. Before jumping into solutions, our idea was to first try with as simple as possible solutions and complicate them along the way only if necessary. So let's keep things as simple as possible. So CPU-based auto-scaling on Kubernetes is the most simple thing you can take. It's super easy to configure target average CPU utilization. We set it to 50%, and we went with it. So imagine that one request needs about 1 second to handle, and imagine that we are having a steady load of 50 requests per second, and that we set the target to be target utilization to be 50%. In that case, we would have 50 busy instances generating these 3D highlights, but we would also have 50 idle instances just waiting there. It works great. However, what would happen if load spikes from 50 requests to 150 requests? From the first second, all 100 instances will become busy, and surplus 50 requests will start choking into Redis queue. From that moment, Kubernetes autoscaling will start screaming for more resources. However, cloud providers need some time to spin up these virtual machines, and it can take up to 5 minutes to have them ready. And during these 5 minutes, around 30% of requests would fail. So we realized that we will have a problem whenever load spikes for more than 2 times. And here, for example, you can see how it goes. We have like a 9 times spike. And in this example, you can check the yellow line indicating that CPU, because of a CPU target, we need 2 times more instances. However, blue line shows that there is a certain delay between yellow and blue line. And here at this point, we have less instances than requests, and which means that we will have problems with latency and skipped highlights. So it was evident that CPU autoscaling can support only 2 times increase. The problem is that the cloud platform needs some time to spin up these instances, and this reactive autoscaling is insufficient for bursty and real-time workloads. So we had to look for another solution which can estimate load somehow and pre-warm our infrastructure in advance. So we had to change our philosophy from reacting to predicting. As I said earlier, almost all matches are scheduled in advance on competition service. And we said that 3D simulation engine load depends on number of concurrently watched matches. So our idea was to scale resources in advance based on the number of estimated watched matches. But how to estimate it? Match viewership varies by time of the day, day of the week, or month. You can see here how it goes, like from 5% to 100%. So it was hard to predict how many matches will be watched at the same time. However, looking at historical data, we realized that match viewership is highly predictable when grouped by competition type. So, for example, in case of friendly matches, we realized that view rate is about 75%, while for Champion League matches, it goes from 5 to 20%. And this is estimated, this could be estimated. Somehow, we can take these numbers empirically. And of course, we could use some machine learning here, but as I said, we wanted to start as simple as possible and make things more complicated only if necessary. So we decided to take these as empirical numbers and to use it, to combine it, to multiply it with number of scheduled matches by competition type to get some estimated number of watched matches. So, and to prepare our infrastructure a few minutes in advance so it can surge that load. Luckily, Kubernetes Autoscaler is extensible, flexible thing. And in addition to CPU, it also supports custom metrics. And since Nordeus uses PubSub, since Nordeus uses Prometheus for monitoring, we decided to leverage that and to expose this estimated number of watched matches on competition service as Prometheus metrics, which would be scraped by Prometheus periodically, which Kubernetes Autoscaler can use to scale 3D simulation engine instances based on that. And to bridge this gap between Kubernetes Autoscaler and Prometheus error, we used Zalando's open source tool, Cube Metrics Adapter. I want to use this opportunity to say thank you, Zalando, for such a great tool. And we could use it to scale 3D simulation engine based on Prometheus instances. We said that we had to prepare our infrastructure a few minutes in advance, but how far should we go with estimations? Since clouds needs up to 5 minutes to spin up new instances, we decided to expose these estimations 10 minutes in advance, and that it will be enough for us to prepare. So let's go back to this example with 9 times spike. Here you can see that 10 minutes before spike happened, our system prepared and estimated with the blue line that it needs more, that it will need more instances. You can check yellow line now. Again, it has some certain delay in instance creation, but it was before enough this actual load, so we were ready for it. What you can notice here is that here we estimated much higher number of requests than it actually happened. So we were over provisioned. And since we are estimating things, it was certainly that we will miss something, because estimates are just estimates. We will miss them for sure. If overestimated, like this, we are throwing money out of the window. However, what will happen if we underestimate number of matches? We decided to use CPU autoscaling as a safeguard. So to combine these two metrics, we just had to ensure that we don't underestimate for more than 2 times. Because CPU as a safeguard can save us with this 50% of target utilization. So it was just important not to underestimate total number of requests for more than 2 times. And our autoscaler, we configured it like this, based on these 2 metrics. So custom metrics based on estimated number of matches, and the CPU utilization, we set it to 60% because 40% of idle instances was enough for us to mitigate these underestimates. And as you probably know, the autoscaler takes the maximum recommended target. And we will happily running this in shadow test for a few months. Everything worked great. Based on estimations, our cloud costs would not exceed 10%. So we were ready for a global launch. And what used to be a most anticipated and high risk release, it turned out to be the smoothest release ever. We just released a new client version, and we, on the backend side, we just had to enable feature switch or feature toggle, you name it, not to send 3D highlights only to Nordeus devices, but to all users. So that was it. We already had all observability in place, and we were ready for it. We set up a monitoring, alerting, whatever needed, and we were ready. Running this, the global launch was successful, everything worked great, but running this for a few more weeks, we realized that most of the time we are overestimated. And that our estimation spins up too many instances. We are under this 10% of cloud costs increase, But we asked ourselves, can we do even better this? There must be a way to do it smarter. So if underestimated, we had the CPU as a safeguard, but if overestimated, we are still throwing money out of the window. So we came up with an elegant idea and said, what would happen if when we estimate new number of incoming requests, what if we take into account actual load, which is currently happening, with what we estimated 10 minutes ago? Let's take that also into consideration when estimating a new number of requests. So we came up with this formula to take into account this difference and like a mistake in our estimation. So system can correct itself after some time. And it was easy for us to configure this in Prometheus using offsets and recording rules. And we tested it, how it works. So let's check this example. Here we are first underestimated the load for 280 requests. And at some point we overestimated. So how this self-correction works. Here in the beginning, from historical reasons before this graph, our estimated corrected metric took into account this mistake of 280 requests from before. And whatever we estimate with yellow line, it adds these 300 requests to it. And you can see it here from 415, estimation goes up, and blue line follows it by always adding this number of requests. However, 10 minutes after, blue line realized that it's overestimated, that there is a difference in actual load and what we estimated, and it tends to align with the actual load. So you can see here how estimate the number of corrected metric, how it aligns with the green line, with the actual load. So it was beautiful when we saw it for the first time, how it worked. So it's a simple formula, and it made it effective. But there was a small catch. We said that we are preparing our infrastructure 10 minutes in advance. And we have now a self-correcting system which corrects itself after 10 minutes. So there was a risk that we will scale down exactly when the load is expected to happen. So we had to, luckily, Kubernetes Autoscaler has stabilization window seconds feature. We set it to 20 minutes. So there is enough time for it to stabilize and wait for actual load to happen and to absorb that surge. To sum things up, we ended up with a hybrid solution. It's a predictive self-correcting autoscaler based on these three pillars: CPU-based scaling, real-time load estimation, and continuous self-correction. Thanks to 3D simulation engine nature, because it's a real time, we could leverage spot instances on cloud and make optimize costs additionally. For those who don't know, spot instances or preemptible instances are much cheaper virtual machines provided by cloud providers, which can be terminated at any point with a short announcement. Like cloud providers will announce it in 30 seconds that we'll terminate it, and these 30 seconds were more than enough for our 3D simulation engine finish current task and to gracefully shut down. So we could leverage that. So we ended up like with all these improvements with spot instances and self-corrected system, we ended up with increase of just 3% instead of a goal of 10%. As Novak Djokovic would say, not too bad. Thank you so much for joining me. I hope that you found this presentation insightful and that you found some ideas that you can apply to your workloads and to optimize your autoscaler. Thank you.
Did you never have the instance that too many spot VMs got destroyed and you got down the demand of the platform?
Oh, great question. So the question is, did we have some situation where cloud provider terminates too many instances in short period, so we end up with less instances than we had? Yes, it happened. Usually we have like it's a huge scale, and cloud terminates 10 instances at the same point, but we still have room because we always have this 40% of idle instances because of CPU-based metric. It's usually enough, but it happened once that they terminated like hundreds of VMs at the same time. It was an incident, but it didn't happen that often. Yeah.
Do you ever run into the issue of not having enough spot instances available by the provider?
Great questions. Yes, we had that problem. So the question is, did we ever have a situation where we cannot? We requested more spot instances, but cloud provider cannot create them. Yes, we had that scenario. How we mitigated? We have multiple node pools on Kubernetes, and our 3D simulation football engine can be hosted on any of these. So it's some kind. We didn't set a node selector to a strict node pool. We just have like tolerations and affinities in place. So if there is no that specific spot node pool, then cloud provider will ensure that it can create another node pool, another instances in some another node pool, and it works like that. Yeah.
So you said the
Amazing questions. Amazing question. This one I have to repeat it because of online audience. So the question is, because we estimate this number of on historical data, do we need to do something special when we have some like a special live events happening in real life, when we can have much bigger audience than and much more watched matches than regular? Yeah, we handle that in that case. Our competition service is aware of live events, and we have option to set like to set some static number of instances we have to ensure that we will have during some period. So we, for example, Germany plays against some other team, then we can set some rule that we will need at least let's say 10,000 instances to add it to all estimations, just to ensure that we can handle some live event. Yeah, I didn't cover it in this presentation, but it's a good question that we actually emitted. Any more questions? I have to check online. I guess there are no questions. Conference organization asked me to share it. Please vote, leave me a feedback, and thanks so much for joining me. Of course, if you have any questions, you can catch up with me here or write me an email or LinkedIn, whatever. Thanks so much.